let's kind of get into plus and minus a little bit and see what all of that really is all about, rather than something you just heard somewhere when you were 12 years old. Okay, basically, okay, all we can do is add with our fingers. Every other mathematical concept has to be derived. As primitive organisms in this world of mathematics, we count, okay, which is a process called addition, okay, which is symbolized by the plus. Okay, so if I have one item and plus another item, I count 1, 2. So 1 plus 1 equals 2. This is something that's innate in our kind of just, animal reality. Now, where Steinmetz comes in is how we work our way out of these type of situations. So the thing is what Steinmetz decided is being that we can only add, because we're primitive creatures. If we want to subtract, we have to use what's called an operator to evoke subtraction. So what Steinmetz did is you take a minus 1 and you multiply that by 1. And if you add that to 1, then you have subtraction, or 0. And he called this an operator. So now, not only being that 1 has no real existence in the quantitative end of it, we can just say now we have the concept of minus. So he's introduced now the mathematical concepts of plus and minus. Okay, and the way we derive these types of equations is we take 1, okay, and we take what's called the square root of it, okay, or we take 1 to the 1/2 power. And this gives us plus 1, as most mathematicians would know right off, and minus 1, because the square has to have 2 roots. So what Steinmetz decided, let's just keep carrying this on so that we can get Tesla's 4-pole electricity into equations. So Steinmetz decided, let's go 4th root of positive 1, which has to have 4 roots. So you end up with 4 roots. You end up with 2 that are the square root of 1, which is plus 1 and minus 1. And you have 2 roots, which are the square root of negative 1, which is plus j and minus j. So now we have 4 polarities rather than 2. We've scaled it up. This is what Tesla visualized in his visions in his mind, but Steinmetz turned it into a very simple algebra. There's no sines, there's no cosines, there's no trigonometric functions to deal with or any of that. It's a very simple algebraic situation. So now what Tesla did when he moved from the alternating current to the impulse current, okay, I'm going to have to define these things now. It's sure a lot of work.
The guy needs a new eraser.
Okay, in the telegraph days, we have what was called continuous current from batteries. In other words, as time moves forward, if we have a device which basically measures the current, it's always the same. It's always constant. Okay, and the chemicals as well as the ether move in the direction of the current and gives us the false illusion that the wire is carrying the current and not the ether in the space between. If we take an electrical condition, let's see how I'm going to go about this now. Okay, well, I'm going to stay with this. Now, if we take this current, okay, what Tesla worked with was alternating current. So now with alternating current, what it is in a constant, where this current is constant, alternating current is in a constant state of change. So that can't really be represented by a line anymore, but now it's represented by a circle, okay, which continuously moves. Okay, and if we take projections of this circle, we find that there's one piece of the wave, one plus minus type of situation, that produces a kind of sideways spiral, which is known as a sine wave. Okay, but the thing is we're dealing with a circle. So what it is we got this other wave, okay, and it's moving in a contrary conjugate type of situation. So at every time the current's not zero, but there's another one to back it up, and they just keep going around the cycle, and that's what makes the motor turn. We start off with +1, and then 90 degrees later, plus J appears, and then 180 degrees later, -1 appears, and then 270 degrees later, minus J appears, and then 360, we're back to 1, so that the piece of iron inside the motor doesn't have to be connected to anything, because now it's just simply following the magnetism around. It becomes the perfect electric motor. Now, what Steinmetz shows is if we take this direct current, okay, and we open the switch, okay, the big problem in electrical engineering in the beginning is when you open the switch, when they built the big substations and the transformers and all that, you can't turn the electricity off. It'll blast. So now Steinmetz had a new job. Why was everything exploding? First, he stopped it from cooking. Now it's exploding. When they got the power level high enough, well, it turns out to be that the magnetism and the dielectric fields have stored energy. And if it has nowhere to go, it will blast a hole to get there. So what it is when you turn off the electricity, if it's pretty much in a direct current circuit and it's not much to store electric fields like coils or condensers or just light bulbs, what it is the current has to change at some rate. It has to move. It has to go into another direction. So what you get is you get what are called transient currents or impulse currents. You get these little jolts and changes as things are trying to readjust. So if I have a current, okay, and then all of a sudden I switch that current, then I get like a spike, okay, and that sudden rate of change is like an electrical impulse. It's not an oscillation or a cycle. It's not continuous. It's a quick change from one step to the other, and the whole electrical system has to readjust to this. So usually what happens, being that there's so much stored energy, that it starts in an oscillation.
I'm sorry, go ahead.
That little tiny segment he drew there, that's the Heaviside step function. That one step, as he says. It's called the Heaviside step function. I have the formula for it, and yeah.
So that was the thing he took out. Now, most people look to keep that in when they do these over unity experiments. They want to trap that energy. You know what I mean? Divert it. Instead of just
stop it before it creates harmonics, I think.
Yeah. Before it creates a runaway resonance.
Yeah, the hysteresis.
Yeah. Let's see.
Crystals. I got something going on with a tourmaline that I've polished like a prism, and then a stone of unknown origin.
I like those. Joe and I talk about those things. When you get one of those weird stones. I love those things.
It was brought to me 38 years ago. It's electrically conductive, and I don't know what it is, but it's obviously man-made.
Somebody's making a battery out of the rocks around you, or what?
No, it was a polished crystal.
Okay.
But I haven't been able, every time the name that was written on the piece of paper wrapped around the cotton ball the stone was in, the guy that brought it to me 38 years ago wanted to make a trade. He thought he had a diamond, but you could tell by the refraction off the light, it was effervescent, so it was not a diamond. And then I read the piece of paper, and I've been looking up what it is on the internet and can't find it anywhere.
Really? You'll have to show it so we can all take a look at it if you have it available.
I'll have to talk to you about it in private, see if maybe you want to do that or not. But I mean, the electrical experiments I play with, yeah, that I can do.
Okay. Yeah, I always like to talk about rocks, man. I love crystals. I love what they do. I love trying to get them to turn on. You know what I mean? Pulse them, hit them with water, do something, put some electricity in there. But then the only thing I ever found is you got to tap it, You got to put it in the sound wave. You got to put it in a crystal-made drum sound wave or a piezoelectric in order to get some of these things turned on and work the right way. Otherwise, you're only going to get tapping with tuning forks.
Right. Okay, I got an experiment that might be good then. I bought this crystal that was poured at some place that was working with them, and it ended up with a line down the middle where the quartz rolled up and made a division line when it cooled. So it looks like an accretion plane, like a galaxy. The sun is 8.2 inches long. That's the wavelength that electrons throw off from hydrogen actions in the sun.
Really?
21 centimeters. 1420 point something megahertz. It's a blue light photon. It's 8 point. And if you look in the pyramids, one of the vents in the side of the wall that's like a microwave conduit, one of the measurements is 8.2 inches.
Really?
So it may have facilitated hydrogen making a maser. It's almost like a laser, only it's a microwave system called a maser. So there's masers using microwaves, and sazers that use sound. They all focus it to an extreme point to where a priest could write the name of a tribe in a gemstone.
Huh.
That's
Those names.
It's got to be plasmoids.
Yeah? Well, that would be interesting. Those names sound like American Gladiators. That TV show. Maser and taser and laser and blazer and whatever azer they got. But that's really cool, though. That would be an interesting thing. You still have that crystal, or yeah? Okay.
Somewhere, I'm hoping. I don't know. I recently discovered a certain piece of paper is missing, and I pulled it out 2 days ago. It's gone. It disintegrated.
Yeah, I love talking about that with Joe. If you get everything straightened out and figure out what you want to do and talk about, because Joe loves rocks and crystals and stuff like that as well. So that's always an interesting conversation.
Well, something 8 inches long should be physically, I could see, people should be able to see the effects if it happens in the lattice.
Yeah, that'd be really cool.
Should show up on the camera.
Nice. Okay. We're going to have to get back to this now, but man, I'd love to see crystals.
Where the energy has to go between the various forms and bounce back and forth to try to get out. And it produces what's called an oscillating current, where the sine waves now are compounded with this other dampening wave, and it produces oscillating currents. Now, these type of currents no longer have frequencies in the conventional sense. This has no frequency, DC. This has a constant frequency, an RPM, which we call cycles per second. But this has a different type of frequency in that you find that these curves, just like these curves always move in a sinusoidal form, these curves always move in an exponential form. And it turns out to be the same exponents that are associated with things cooling off or leaking or any type of dissipative type of phenomena. It never occurs at a constant rate, but it occurs like gravity on a rate upon a rate. And it also is a frequency of types, but it would be called an imaginary frequency. And instead of being in cycles per second, it's what's called in decibels per second. Now, the generalized electric transient will be some combination of those, and will produce this complex frequency. So these things are all running up and down the transmission lines and getting in the transformer coils and motor coils and starting fires, and sparks would just jump off of the lines and hit people for no apparent reason and blast them out of existence. It was a real problem. So Steinmetz wrote his second book, The Theory and Calculation of Transient Electrical Phenomena. And out of this book emerged this understanding of electricity that is so far in advance of anything today that it's just mind-boggling what this guy had discovered. And this, again, is what Alex Anderson had to work with in the development of his radar. Now, what Tesla did is, in using these impulse currents and oscillating currents in his engineering, Tesla came up with another type of polarity situation where there's only one pole. That's it. In other words, it's not even the square root of 1 anymore. It's the 1 root of 1, which is just 1. There is no plus and minus. Tesla came up with an electrical device where he could connect it to something like the Earth, and it would create electrical movement in the Earth, but it wouldn't have anything else to connect to. It was a one pole. It was just simply a plus. There was no negative. There was no return circuit. Because the situation is like I explained, if you're going to transmit electricity or receive electricity out of the ground, you put in 2 ground rods in the earth, okay, and you connect these to a battery. The telegraphers tried it, and that's the first thing they found out is most electricity just goes between the ground rods. Now, if I make that alternating current, well, it's just going to be the same thing. I can make a quadrupolar alternating current, then you got 4 ground rods. All it's going to do is spin around inside. So the problem is how are you going to do something where you can transmit into the earth and not deal with the circulatory effect? So this is where Tesla's researches and writings and work are most important, is how did he accomplish this? And the implication out of this is the existence of another space called counter space. Shortly after these things started being developed, a guy by the name of Rudolf Steiner started to come up with a way that the mathematics, him and his followers, would get into this what he called a counter-spatial situation. In other words, now there's not just one space, but there's 2 spaces. And it's very similar to this addition and subtraction situation. Now, the thing that makes electricity so interesting and worth studying is the fact that electricity, and always being a 4-pole situation, exists in never any less than 2 dimensions at one time. There is no electricity unless you have magnetism and you have dielectricity. Otherwise, it's just magnetism and dielectricity. Until the 2 are united in some type of geometric configuration, you do not have electricity. So what Tesla had done was, with electricity now, mathematically, electricity gives us a situation where we have to have plus 1. In other words, we have to have 1 multiplied by positive 1, where we have negative 1 multiplied by positive 1. So it gives us our positives and negatives. But now in another situation, we got this counter space situation. Now we have to figure out how to express that. Well, now we got 1 to the plus 1 power, and we have its conjugate plus 1 to the minus 1 power. So now we have taken a step from addition and subtraction to now we have multiplication and division, which is a more compounded, abstract type of process. And it's always in a logarithmic form. It's not in a linear form. It's not additive. It's compounding, cumulative in a certain sense. It's a situation like 1, 2, 4, 8, 16, 32. It's that type of situation. So what electricity implies is this is our spatial, because multiplying is usually your spatial deal, where addition subtraction is your time deal, is in electricity, unlike in physical situations or physics situations or anything where you're dealing with regular matter, is now you have electricity that goes forwards in time and you have electricity that goes backwards in time. You have electricity that exists in space and you have electricity that exists in counter space. So any electrical situation has to have these poles or polarities in order to be electricity. Otherwise, it's just one end or the other. Now, to get a little more into the erasure process here, get into kind of how this electricity behaves. So I'm trying to make a step at a time. I'm trying to make it less abstract. This is a good time for questions. I can hear. Yeah.
Well, I always think in terms of nonlinear space-time. So how does because I find this really intriguing. So if one assumes that space-time continuum is nonlinear, evidence kind of shows us a little bit, then would that also affect the behavior of this bidirectional electrical activity that goes forwards and backwards in space and counter space? I mean, how do you see that model fitting into it?
Well, that's what I'm going to get into, how that actually manifests physically using pieces of metal.
Because this kind of suggests that the Philadelphia experiment, not to harp on too much, probably was sort of maybe a clumsy, but kind of nibbling at the edge of this concept. That's kind
The
of
Philadelphia experiment, being that naval engineering is kind of part of my work. If somebody pointed a gun at my head and said, "You're going to do this, or we're going to pull the trigger," you figure it out. Okay. The first thing I would do is I would get my hands on the anti-mine cables that run around inside the ships. I had a Navy minesweeper to take apart once. Actually, we were supposed to put the thing together, but as usual, human geekdom destroys all projects. So a beautiful piece of naval engineering went to the scrap yard. But this thing was filled with cables, that the purpose of the cables was to make the ship magnetically invisible. Okay?
Yes. But I'm just saying that since very recent evidence has not proven these system gravity waves and that space-time is
Oh, but yeah, you know.
and that space-time can truly be shown to be nonlinear, then it kind of gives credence to this idea that you would have space, counter space, and sort of time, anti-time.
Right. Well, see, the thing is, I don't in this period of time and mentalities and all that, not really thinking so much of time, space, because I haven't really combined them together yet. Because then I have to use a differential equation where not only am I varying with respect to time, but I'm varying with respect to space. So I might try to push that far, but right now I'm just kind of,
Let's start with groundwork.
Yeah, okay, yeah.
Yeah, I wanted to ask about the ether, whatever you want to call it. But right now, the ether is equal to, it's related to, the permeability and the permittivity of free space, which is equal to 377 ohms. Is this thing true for all scales of size? I mean, somehow, if things are really small, would it be not 377?
No, you're stuck with it.
I mean, are you claiming that it's 377 ohms?
Always 377 ohms.
Regardless of scale?
Right, it's always 377 ohms if the speed of light is always 2.998
Yeah,
centimeters per second.
There's a thing that refutes this.
But if the speed of light changes, the ohms change.
Yeah. Now, there's
Now,
a thing about,
in a simple transmission structure, that is no
but that's
longer
on
the
a
case.
macroscopic scale. Now, for example, glass lenses, which you're all familiar with, focus light. But if you put an X-rays through it, it doesn't focus X-rays. You can move the lens back and forth. It's just sort of darker in the middle and lighter on the edges, but it doesn't focus X-rays. There's something happening because the X-rays are even smaller or doing something.
Well,
different.
according to Tesla, Tesla insisted the X-rays were not transverse vibrations, so they couldn't be influenced.
But they're all electromagnetic radiation.
No, they're not. Tesla said that X-rays are not electromagnetic radiation. And there's a big controversy over that. And two whole systems of X-rays developed, the Tesla system and the General Electric system, developed where Tesla could stand in front of his X-ray tubes and not be killed, where if you stood in front of an equivalent X-ray tube of the GE design, you went to the grave.
Well, what is the difference between the Tesla X-ray?
Well, that's kind of right now out of the scope of the conversation.
Yeah, but
And nobody really
qualify
said.
it, because X-rays are done by slowing down electrons or slowing down.
Well, we'll get into. I'm going to try to get into the electron. That's Tesla. I'm trying to get to Tesla's last discovery, but there's so many. I got to kind of stay on a certain path.
Yeah, okay.
I can't just give an 8-year college course in a matter of an hour.
Yeah, but this next question is much more simpler. It relates to Tesla thing. We have a device, which I don't know if you've ever heard of a thing called a toroid.
Yeah.
Which is I often refer to it as a Buddhist, kind of like a Buddha belly with a very large content kind of thing. Because in a toroid, unlike a solenoid has magnetic field that goes outside of itself.
Right.
Whereas
Open circuit. Toroid's
is a
closed circuit.
completely satisfied and very content kind of device.
Right.
Which has all the wires go around completely around a circle and nothing sticks out of it.
The natural form of magnetism.
Yeah. Well, now the thing about it is you take a magnet, you say you have a large toroid, and it's energized by 60 cycle 120 volt, it's like half of a variac or something.
Mm-hmm.
If you put a magnet in or around the thing, the magnet does not vibrate because there's no magnetic
field. No external
magnetic
magnetic field. Right.
Contained within the body of the toroid core. Now, what is going on when you take a wire and you run it through the middle of the thing, which has got no magnetic field, and around the outside heavy gauge copper wire and you short the wire, you're forming a loop that goes through the middle of the toroid and around the outside, and the wire gets hot and the Buddha belly, the Buddha gets angry because now it expresses anger into the wire. But it's not, the wire's not immersed in a magnetic field. It's because the magnetic field is only going to the core.
Well, the magnetic field associated with the wire has to expand out into the core. In other words, the lines of force of magnetism around the wire are concentric circles, and the core has got so much permeability that the circles just stay in the core. But there's a thing about magnetism, so you're bringing out, is that the physical relations of magnetism as we use them don't add up.
Yeah.
You just pointed that out.
Yeah,
They don't, the toroidal core, it doesn't add up. There's some way and that's where this counter space comes in. There's some way that the wire, see what you're describing, what you've done is you've made one turn around the toroid that's now shorted out.
Yeah.
Okay, when you do that, the magnetism, that's what I'm going to get into. Magnetism can't get out of the short, it's trapped. In other words, if I have perfect wires, okay, and I got current flow and I jam those wires together, the magnetism that's stuck in between those wires can't get out because there's no resistance. There's no counter space to eat up the magnetism. It's stuck. That's the classic zero, what do they call it? The absolute zero thing, where you take the lead disc, okay, and you drop it through the liquid helium and let it get cold. And when it gets down to absolute zero, because the intermolecular stuff can't interact with the electricity anymore, it will float on the magnetism because the magnetism can't get through it. But the thing is the magnetism is not going through the wire like it's spreading out into space. What the magnetism is going into the wire, into an inner space, a counter space. See, that's what I'm trying to get at. In order to understand electricity, you have to have an understanding of counter space, or it's impossible. And you have to be able to deal with a situation where things are coming from the future into the past, as well as going from the past into the future, because the electric wave you're working on is the point at which all these things cross in space and time.
One more theoretical question.
Yeah.
I think this is really fascinating. And the recent experiments with Bose-Einstein condensates, where they can get light to slow down almost to like a few inches per minute. What do you suppose would happen to your space, counter space, time, sort of anti-time realm? I mean, do you have any thoughts about that? I'm just kind of curious. About this
Well, what I want to see is what would be if the product of the two was a certain velocity, then what impedance is the ratio of the two? How does that change?
But I mean, this would be like an area of experimentation. I would think would be sort of interesting, like another handle to sort of open this box up with.
Well, I mean, basically, if you add more inductance coils along the path and you add more capacitors across the path, you can build a transmission line and make a wave propagate at any velocity you want, or make the velocity even go away.
So are you talking, Victor?
Can you back that up like 1 minute?
Yep, absolutely.
This is a really good lecture.
Yeah. Oh, yeah. It's
He just
probably one of the
question that
Okay. Let me see if I got it.
impedance.
It out.
Yeah.
Okay, when you do that, the magnetism, that's what I'm going to get into. Magnetism can't get out of the short, it's trapped. In other words, if I have perfect wires, okay, and I got current flow and I jam those wires together, the magnetism that's stuck in between those wires can't get out because there's no resistance. There's no counter space to eat up the magnetism. It's stuck. That's the classic zero, what do they call it? The absolute zero thing, where you take the lead disc, okay, and you drop it through the liquid helium and let it get cold. And when it gets down to absolute zero, because the intermolecular stuff can't interact with the electricity anymore, it will float on the magnetism because the magnetism can't get through it. But the thing is the magnetism is not going through the wire like it's spreading out into space. What the magnetism is going into the wire, into an inner space, a counter space. See, that's what I'm trying to get at. In order to understand electricity, you have to have an understanding of counter space, or it's impossible. And you have to be able to deal with a situation where things are coming from the future into the past, as well as going from the past into the future, because the electric wave you're working on is the point at which all these things cross in space and time.
One more theoretical question.
Yeah.
I think this is really fascinating. And the
I
recent
have a 5D
experiments with
form for the
Bose-Einstein
spacecraft, too.
condensates, where they can get light to slow down almost to a few inches per minute. What do you suppose would happen to your space, counter space, time, sort of anti-time realm? I mean, do you have any thoughts about that? I'm just kind of curious. thought about discussing.
Well, what I want to see is what would be if the product of the two was a certain velocity, then what impedance is the ratio of the two? How does that change?
But I mean, this would be like an area of experimentation. I would think would be sort of interesting, like another handle to sort of open this box up with.
Well, I mean, basically, if you add more inductance coils along the path and you add more capacitors across the path, you can build a transmission line and make a wave propagate at any velocity you want, or make the velocity even go away. That's, but let me get into, I want to get into kind of, because nobody knows what I'm talking about right now, okay, other than the history stuff. Okay, I'm sure there's a few people around, but I mean, it's, what is magnetism? You know what I mean? What's a volt? What's an amp? What are we talking about? Velocity. What are all these things? Okay, so that's what we need to do. That's what I gave you the history. Okay, the reason for getting into these guys, okay, is Tesla found out a way to get out of space and connect to another dimension. And Alexanderson figured out a way to circumvent space completely, or his work implies that you can circumvent space completely and make things appear in one other part of the universe without anything time delay in between. Now, if I want to talk to Alpha Centauri, I sure in the hell am not going to use waves that propagate at the velocity of light.
Oh man, thank you, God. Oh my God.
Okay. All right, Victor, your camera turned off. What's going on over there? Oh man. He just had a big revelation.
Yeah, some kind of epiphany.
Yeah. Well, let's see what he's got going on, man. Everything kind of shut off on him.
He might need a moment to process.
Oh man, that's so cool. What do we got going on over here? Yeah, he was. Yeah, he just had a eureka moment. We're kind of hoping he comes back online soon so we can all share in it. There you go. Akabee knows what's going on.
Sorry. Yeah, that was good. I just watched this twice a few days ago. The third time around, with the added energy and field of everybody, and the text over here, Society of High Sciences. You know some shit. Yeah. Anyway, I thought I was crazy thinking that these spaces that I'm seeing in the numbers are real.
Yeah.
And he just confirms. So if the master says that this, it just dawned on me how it all fits. And he just said what I told you earlier. I needed to take my equalities and start cross-producting them.
Okay.
And his question is, what would the impedance be for these velocities? It's hidden in the 1/137.
Huh.
So the fractal, I got to open up that 1/1 and work the whole damn thing out and then start cross-producting to take to the next level. And I've already got the pressure gradient figured out, golden ratio. So it popped.
Nice. That's absolutely amazing.
That's awesome.
You gotta love it, man. I love watching this stuff with other people, man. This is so cool. Victor, I hope it all works out when you start working on it, man, because it sounds amazing.
Well, impedance in radio is looked at the permittivity value, E, that E sub 0. You got permittivity and permissivity or something. I'd have to go look at the two anyway. You can get the speed of light from that, and it's part of the 1/137 because it deals with the energy of an electron. Yeah, and angular momentum and induction. Yeah, so we're looking at capacitance and inductance to give that frequency of the temporal drill and the whole bit. Yeah. And then the dimensions for teleportation, it's there. All three, Tesla's drill, Steinmetz's teleport we now have proof of quantum entanglement. So you can entangle a microscopic with a macroscopic object, people. It's been done. Permeability and permissivity. Yes, permissivity. Permittivity, permeability. There's so many factors, but they're all the same thing. Resistance and capacitance, more or less. Society, yes.
We have like the smartest audience ever. You noticed that, right?
You've got a group. I mean, oh my God. Yeah. And then I have a pulse generator that I've been working on. My mother showed me something she learned from her mother. And when I was 7 years old, they gave me this toy to play with. And while I was trying to figure out how to make she told me to pull a shoestring out. I found this big button and I laced it up. And you can pull on the string and make the button contra-rotate and spin.
Okay.
Well, at the same time, she was telling my sister to go pick daisies, and she was making a wreath for her to wear. And when I saw them too, I thought if the disc was a magnet and the wreath was a coil, and ever since I was 7, I've been playing with that whole, continuous dollard.
Gotta love it, man. Gotta love it.
Use Tesla's waves, I would have to have an electrical permeable medium of such capacity that it could handle the flux density to carry the power from one end to the other, and that wouldn't be a likely situation between here and Alpha Centauri. So the only thing I could do was build electrical devices that responded in a scalar manner with regard to space. That way I could communicate with distant ends of the universe without having to wait for the signal to get there.
This is where the Alexanderson model.
Yeah, and the Integratron. The Alexanderson model, because you went through this and you're down there, the Alexanderson antenna is an analog computer of that situation. Now, what I'm finding is, which is striking with these analog computers, is not only can I get the waveform or the mathematical function, but I also get the physical effects without the Tesla coil, without the Alexanderson antenna. That is what I would have never expected. And that's what's fascinating, because you might not even have to build all this stuff. All you need is a box full of coil capacitors.
I would love to see this in a cryogenics lab, actually, but that's a separate topic.
So at any rate, so what we're talking about is electricity. Let me change colors here. Maybe this one will erase easier. I'll draw lighter. Okay, so let's come up with a dynamical situation that everybody can relate to, because they all drive. Everybody here drives an automobile, or has been in one. So what we're going to do is we're going to use that as our model. Okay, and we're going to analyze it dynamically, just as we would all these electrical things I'm talking about. Okay, so now what we decide to do, okay, is if we're moving at a speed, okay, and then all of a sudden we decide.
All right, Victor, you having another aha moment over there? I can see it on your face.
He just confirmed me. I just said it's all going to basically boil down to capacitance and inductance, and he said you can throw out all the coils and build a box with capacitors and inductors.
Nice.
He just proved my. Oh, this is beautiful. Let's continue.
Oh, it was well worth coming on today, wasn't it? You got all kinds of stuff. You're muted again.
I was just saying, yes, it was great, and it's Sunday. Thank you, God.
Yeah. Big man upstairs got a lot to do with it, man. You know, the more we get into our coils and stuff, it's always turning out that way. I don't know if you noticed that. Everybody kind of has the same understanding of everything in the Bible and the numbers and all this stuff. We're all kind of on the same path. All right, let's watch some more. Let's see if we get Victor to get another aha moment over here.
Okay, and then stop. Now, all kinds of things happen when we do this. During this interval of time here, things happen that are measurable. Okay, now if the speed increases at a constant rate, what we get is we have a force pushing us, okay, which all of a sudden becomes a constant force, okay, pushing back. And then when the speed change is over and we're at a steady speed, this force disappears, and then there's no more perception of movement. Now, another thing happens. If we measure the quantity of gasoline in the gas tank, okay, and there's 100 cubic centimeters before we start, and there's 50 cubic centimeters after we execute this function, then not only do we have this wave in time, now we have this little cube in space of gasoline that doesn't exist anymore. In other words, we have this force that appeared and disappeared, and we have 50 cubic centimeters of gasoline that went somewhere and is gone. Now, this is what's called differentiation and integration. This is calculus. Okay, this is how Newton and Leibniz and these people, they wanted to find the relationships between these situations of why you have this integrated situation where you have the accumulation. In other words, the gasoline just doesn't disappear at once, but it accumulates or deaccumulates. In other words, it's an averaging process that weighs something that you can hold on to. Now we have this time differential here, which is kind of abstract. It's like only there when we're changing velocity, and then it's gone. So now if we take the weight of your body, okay, and we symbolize it by the Greek letter phi, okay, now we take this, you put a scale against your back in the seat, and we take that, okay, and we symbolize that by the Roman letter E, okay, and we take this interval of time here, and we call that T. So this is the weight of your body, okay, this is how much perpendicular weight there is pushing back on the seat, in other words, the reactionary weight, and this is the time in which this happens. Well, lo and behold, then we have a situation where we've analyzed algebraically what's going on with a very simple mathematical ratio. In other words, your weight as a ratio to the time involved in changing your velocity gives you a force E. Now, what I can do without any changes at all is this Greek letter phi represents a quantity of magnetism. Okay, the time t represents the change in that quantity of magnetism, whether I'm turning the current up or I'm turning the current down or the magnet's moving or whatever. And that gives me what's called the electromotive force E. So now everybody here understands Faraday's law. It's that simple. So this is how electrodynamics and electromagnetism were created, was out of this simple relationship. If I have a quantity of magnetism and I vary it with respect to time, it gives me something appears, an electromotive force. Now this electromotive force then can be taken and applied to another situation, and then we can start to compound this stuff out. Now it turns out there's a pair of these equations in electricity because electricity is working in two dimensions. So we already know about magnetism. We know also electricity has to consist of what's called the dielectric or electrostatic field. So now we have two quantities. We not just have the weight quantity and the single process, but we have a pair of these things. Now, if I take and use the Greek letter psi to represent the electrostatic field, and I vary that with respect to time, and give the rate change the letter I, now not only do we have the electromotive force, but we have the current. So if I take a quantity of electricity, which I'll represent by the lower letter phi, it consists of two parts, or it can't be electricity unless both parts are present. There's got to be a magnetic field, and there's got to be a dielectric field. And these are the two components. The magnetic field exists in electromagnetism in the dimension of space. In electromagnetism, the dielectric field exists in the dimension of counter space. So the electricity is always in one of these two dimensions. Okay, now if I take this quantity, the lowercase phi, then that becomes a symbolic representation of electricity. In other words, that is the ether in its electrified state, and it has dimensions. Because everything we're dealing with, there's dimensions. We have the dimensions of time. We have the dimensions of magnetism. These are what are called dimensions. So it turns out to be the dimensions of this are defined by something called Planck's constant. In other words, this quantity can only exist in integral multiples, which gives further justification to the lines of force theory, because the lines of force have definite size in some dimension. So the electricity can only exist in steps of these dimensions because electricity is made out of lines of force. So I can't have 1 and 4256 units of electrical induction, because it's got to be some kind of, how would you say, like a whole number. It's got to be in these steps, the whole number being Planck's constant. If we make that, a constant or a number, or just make it 1 in our equation. That's what Steinmetz did in order to make his 24-page equations into a little one-line algebraic relationship. All as Steinmetz did is, instead of giving the waves in velocity, he gave light seconds. And once he used light seconds in the equations, instead of the normal, lengths and times, but used that quantity, everything dropped to dropped to 1. Once that was unit value, then all these the space-time continuum equations you were talking about, then all reduced to either the dimensions of space or time, and you didn't have to be stuck in both dimensions to do your calculations. That was the only way that Steinmetz could represent these waves that were bouncing up and down the transmission lines, that there just didn't seem to be there's no way you could measure them or calculate them. It's like they were in another dimension. They were all trapped in these time dimensions and space dimensions, and it made them appear not to be there. So these two quantities we can derive. We break this down, electricity, into its two parts. Okay, now in electromagnetism, these two things have they have what's called a conjugate relationship, in that one is the denial of the other. And that's how one can be calculated from the other. And this is what gives us the Maxwell velocity of light situation. So if we take this electrical field, let's start to see what the electrical field looks like. We're going to start with electromagnetism, because that's the one that everybody knows about, and that's what we're using, so there'll be no argument or mystery. Okay, what I have is I go out in the street, and I look down there, and I see these two black wires up on the poles. Okay, the old 1800 municipal railway DC wires still run down this street. That's Fulton here. Okay, so we're gonna see what's going on with these wires. Okay, there's 600 volts in these wires at 2,500 amps. Okay, which is kind of cranking. Those buses draw a lot of juice. So we're going to do, these wires, they sit on these pieces of wood, which are referred to as insulators.
I'm sorry, how many volts?
600. The feeders are 5,000 amps out of the rectifier. By the time they get here, it's probably more like 500. But if you look at the insulation all burned off, you can see that these things have been jammed up to about 2,500 amps. Okay, so what I have is I got a place that produces the electricity. Okay, I don't know where the rectifier stations are anymore. There's one back here down somewhere between Fulton and Geary, where the juice comes from. Okay, it's going down the road in between these poles to the buses, okay, that are down at the end of the street coming up here. And it produces all these kind of effects. Okay, what it is the wires are trapping the electricity, so it can only go this way, only go down, up and down the line. Okay, it can't go over here or there or whatever. It's got to go one way. There is no electricity flowing in the wires whatsoever to speak of. It's non-existent. It's in the space between the wires. So now if we take these two conductors and we take a nice sideways chop, so we don't have to look at the length, okay, we find that around these pieces of wire are circulations of ether. Okay, and one circulation is in one direction and one is in the other direction, because we have a basically plus and minus type of transmission situation. This is called magnetism. Okay, and it's there. Everybody's held magnets and pushed them together and has felt this thing that's in between the magnets. the like poles is the best because you can feel like a jelly as you try to push them together. There's definitely something there, and it doesn't fall to the floor when you take the magnets away. So there's no mass. So what this does is it creates a concentration of magnetism in the space between the wires that predominantly moves vertically, okay, at right angles to the power flow. Now this magnetism physically pushes the wires apart. So in other words, when all the buses are running, the wires are going to be a little farther apart on the spans between the poles than they are when all the buses are stopped. So there's definitely some kind of pressure or something exists in between here. Okay, now the thing is the further I spread out, let's take one span as our differential element of these wires. Let's say about 150 feet from pole to pole. I take that section of cable and that's all I'm going to look at. Okay, there's a quantity of this magnetism in between these cables, okay, by this circulatory ether condition, pushing the cables apart. Now, if I let the cables move apart, or I spread them apart more by putting in another insulator, moving all the cables over, now this will hold more magnetism, obviously. Now, if I put a chunk of iron or some kind of magnetic material in between those wires, okay, that magnetic material is going to suck in the magnetism, and again, there'll be more magnetic storage capability inside this electromagnetic structure. But with the iron, if I keep increasing the current situation of the magnetism so that the iron can't hold anymore, the iron goes into what's called saturation, and it will no longer hold any more magnetism, and all the rest of the magnetism that's produced by the generating station will have to continue to exist outside the iron. It's what's called a saturation condition. All these things are completely archetypal of space. You can only jam so much in the bottle. Okay, you can only fit so many cars in the parking lot. These are all normal properties of space. Okay, now we'll look at these wires a little further. Okay, well, not only are we dealing with the current of 2,500 amps, but we're dealing with a voltage of 600 volts. Because we got to have the volts and the amps. We got to have the magnetic and the dielectric before we have electricity. Okay, now these lines of force, if I take one wire and focus in on it real close, okay, the magnetism goes around like this in perfect circles if the wire is a perfect circle. The dielectric is completely contrary. It's conjugate. If everywhere in space a magnetic sectional line of force has direction, the dielectric field will always be at 90 degrees of that, and there's no alternation of it possible. So we have where the magnetism is concentric, the dielectric is radial. And this, if one is one way, the other is the other way situation. This conjugate situation always exists everywhere in space. So if you know where the magnetic field is, you know where the dielectric field is. Okay, now the dielectric field, where magnetism has to form closed loops of a circulatory type of fashion, the dielectric field is radial lines that contact the metal surfaces. So they come out and they arch. And everywhere in space, they're at right angles to whatever magnetism exists. So now we have another field of force that exists as a conjugate to the magnetic field of force. And the two of them make up the electric field. Okay, now these forces, the more I raise the voltage, the more it wants to pull the wires together. Not push them apart, but pull them together. So the force is opposite. Now, if I move the wires closer together, these electrostatic lines of force or dielectric lines of force become even more concentrated. So now that I've moved this section of transmission line, the wires close together, the closer the wires are together, the more electrostatic energy the system will store. And it tends to pull itself together, where in the magnetic, the more magnetism there is, the more it wants to push the wires apart and make itself bigger to store the energy. So now we're starting to get into the concept of counter space. We've entered the counter space logic right now. We have two spatial conditions. Okay, now if I take and put a piece of glass in between these wires, like I did the iron bar for the magnetism, the glass will absorb up more dielectric lines of force, and the energy storage will be greater. Now, if I keep turning up the voltage to the point where the glass starts to saturate and can't handle anymore, what happens is instead of pushing the lines of force out, what the glass will do is start to draw even more lines of force in until the point in which it blasts. That's when you get sparks across power lines, lightning discharges, that type of situation. That's what's going on. Now let's take a lightning discharge as another flux example. Okay, we got the clouds, we got the earth. Okay, now because we know about these lines of force, we know that there's this volume of space, of ground and thundercloud that is filled with a quantity of electrostatic lines of force, okay, which are basically trying to pull the cloud and the earth together. Okay, now what happens is the cloud evaporates, the water, which is holding 50 times at least the amount of lines of force that air can hold, is releasing this electricity and it has nowhere to go. So what happens is these lines of force start to become tighter and tighter. And what it'll do is it'll start a saturation in some spot of air, just like in this piece of glass. When I kept turning the voltage up, it'll start to spark inside and then it'll blast. And so the atoms start to break apart at the point of saturation and you get a breakdown zone. And what happens is when that saturates in a counterspatial, yes, there's something you want?
Step maybe away from that board for the camera.
Oh, okay. Thank you. Yeah. Once the saturation process starts, all the lines of force will come running into that and discharge the complete 1 cubic volume of electrostatic lines of force in one fire column. Saturation is complete and total. There's nothing jumping from the cloud to ground or any of these types of, those are all myths. If you build your lightning protection system on that, you're more than sure to get blasted.
What did you say it was doing?
It's a saturation. It's moving in sideways. It's like if I have a bottle full of water and the water represents the electrostatic field, okay, and then all of a sudden the water or something starts to break down like in the middle and the more water rushes in to make what was gone. It's like the whole jar of water collapses upon itself into nothing. And the energy density is so high at that point that the fire appears. And that's why there's the blast. So lightning is not moving vertically, it's a saturation collapse coming in horizontally, and it produces this what's called impulse current.
It's all the static meant into one line.
Yeah, it's a saturation into counter space. Okay, now when I'm sending the electricity down this line, what's going on, okay, is everywhere one of these lines of electrostatic force and one of these lines of magnetic force cross, there's a code joining. You have a process of multiplication. It's basically the symbol of multiplication, the cross, which takes us back to that polarity thing. Again, it's always the four-pointed cross. It's an Indian archetype, actually. At that conjunction point, in space and counter space, is produced the electromagnetism, which moves down the line, and this is what's represented by Planck's constant. This is the product of the electrostatic and the magnetic lines of force, and this is what exists in quantum steps. And this is what propagates at the velocity of light. What rate the magnetic lines of force and the dielectric lines of force move has never been determined. Okay, the equations exist in Steinmetz's book to make the determination, but nobody ever followed through to do the experiments. But they necessarily have to be doing something because the energy is moving. So the movement of the lines of force and the energy, what they do is they're scraping into the wire because the wire is not a perfect conductor, so to speak. But the wire is not conducting this. The space is conducting this. The wire is a reflector. That is basically why all electromagnetic boundaries use a material which reflects light for the so-called conductors, and it always uses a material that absorbs light for the so-called insulators. All electromagnetic boundaries must be capable of reflection, or they will not work.
Wow.
That's the basic engineering principle. I'm sure there's some modern plastics that'll do something, but this is the basic process.
Ben, was that you?
Yeah, that's a big revelation for me.
Go ahead. Tell us all about it.
No, just the fact that conductors are reflective and capacitors are they absorb light.
Okay. You do notice that they put the two wires apart and you got a pure charge state in there. And that's how they're moving it down the line. So when we go to look at people who are doing this experiment and they put it on the scale and they said they're some kind of a plasma thing or something else, it's not. He just explained it right there that it's a pure charge state. That's what everybody's looking for when they go to put it on the scale. When you see NASA's program into that and you see those little styrofoam things he was building, this is the state he was looking for right here. When they're pulled far enough apart, you get a pure charge state. That's what it is. So it has a big thing when it comes to distances between the two wires and why it's there. And he calls it the dielectric, or Steinmetz calls it the dielectric right there. That's so important because your scale is going to go down by massive amounts, or I should say, will have a massive pressure put upon it when you can get to that state. That's the thing. That's how you go from grams to pounds of pressure put on something. You have to understand that state. That's kind of one of the best things I've ever heard anybody describe in this. And it absolutely is a phenomenon and it absolutely works. I've done it. So it's one of those reasons I don't put a bunch of amps into something in order to get it to go on the scale, or I don't put a lot of mixed voltages in it. I put a very, very thin amount of amps in it and a lot of volts. And that's how you get to that state. So it all has to do with if you could take high voltage and make it do that. I just found it so interesting because in every lab test it shows it.
Yeah, I also think it's interesting that he said that the math is there for somebody to do the experiment and nobody has.
Yeah.
It's a missed opportunity right there.
Yeah, there's so much math in there that I don't think they know where to start. But then they don't. I'm sorry, what was that?
I said I definitely wouldn't know where to start. Like I'm probably only a handful of people in this entire world probably would.
Oh, well, yeah, you got to change the frequency in order to control the temperature, and then you're good to go. Then you can get to that state. I do it all the time. I got circuits that do it. So, yeah, this is really something that's you're going to have to understand when you get into the more higher electricities and stuff like that. That's why the plates on my Graviflyer work the way they do, because I control that. I don't just control the distance. I'm not out there with a wrench every 5 seconds. I'm over there doing it with my voltage. I can control what field I'm in based on what I put into it. So it changes the understanding of what you're doing. That's why I get so heavy on people, and learning it, because you have to know it.
You know what it reminds me of?
What's that?
I think it was Descartes when he was talking to people. I think it was something to do with a girlfriend. I think he said something about, if it were possible for me to stand on a plate of iron and throw a magnet at the moon and lift me to it, I would go there to give it to you. And Eric's talking about transmitting this energy to a certain spot. And I'm wondering if we could teleport there and receive the energy to then throw it again and get there in time to catch it. And
like a relay. Yeah, like a relay. Yeah, that would be, I'm sure it's possible. You just got to figure it out how, all right?
Impulses.
Yeah.
That's
We can
so
go
cool.
super aluminum, and we can get to the signal to receive it that we transmitted.
Mhm.
Kind of like the way condensed matter can have a carrier wave on the laser beam pop out before the laser enters the condensate.
Right, and we'd be able to teleport matter without having to disassociate the matter, right?
Hopefully.
Yeah,
I don't,
hopefully. That's what I'm hoping too.
but maybe it's relative. Maybe when we're in an excited state, our mental picture still keeps us. Of course, once you're inside the bubble, you're not affected. You're disconnected from the entanglement, or you should be.
Well, you're right.
You
The
should
brain,
be a fully autonomous particle at that point.
yeah, the brain is just an antenna for your consciousness, which exists everywhere, right? So I guess in theory it would be fine.
Well, what I found interesting was they were talking about that radio, right? And it's an analog, and you call it an analog computer. And then you see throughout history, whether it's the stones placed in certain spots where they go 1 1 1 1 nothing, 1 1 nothing, 1 1, and they keep doing that, and you'll see it in the ground, like in England and stuff, that they do that, and you always look at it and go, well, that's a bunch of ones and zeros and stuff. Were they trying to call somebody? You know what I mean? It may have no relation, but I always thought it was interesting. And then the first computer they had came out with ones and zeros, and that was it in England, right around World War II, that they had that, and they had that computer, so it was all analog.
Turns out Stonehenge was just an ancient giant rotary phone.
Trying to dial home all the time.
No, that's an interesting point. That's very interesting. Beat note frequencies, right? You guys talk about those?
Exactly.
When you are dialing the telephone, it actually has a set of frequencies. DTMF is dual tone modulated frequency. It takes two tones to get the one pulse that goes over the phone. So it is actually a beat note frequency.
Oh, that's interesting. Huh.
I didn't know that. That's cool.
He said that's a big phone.
ET, phone home. Oh.
Well, we're talking about dialing into the dimensions here. We're talking to Alpha Centauri. We got to have a big phone. Oh, man, that's so great. Oh, all right. Let's see what Dollar's got now.
Between two mirrors. But the electricity is of such a dimensional nature that it doesn't have to be complete. It doesn't have to be big mirrors. It's just the presence of the cables is enough that nothing can get through them. Okay. Now, the thing is the electrostatic lines of force tend to embed themselves in because they have to make contact with what are called electrons and protons, which are the ends of the electrostatic lines of force. In themselves, the electrons and protons have no material physical existence. They're terminals of this type of electrostatic condition, and this is where the theory of relativity collapses, is in this particular aspect of what's going on with the electricity. So being that all this is in a speed of light commotion, traveling down the lines, it's dragging through the wire. And then the wire basically burns up the electricity, and there's a sympathetic current flow in the wire that cannot move anywhere near the velocity of light down the line. And it's a situation quite analogous where if you're going down the road in your car and you got to slam on the brakes, what happens is as you skid down the road, it makes a sound, okay, which is called enharmonic. It's a distortion type of sound where energy is being destroyed or consumed. And part of the road will be carried along with the car, but not at the same rate as the car. It will always, the pieces you rip up will always fall behind, and the skid marks will always be left behind, but there will always be the tendency to move. And this is why the wires get hot and give the indication of current flow, but the current flow is the rate at which the electricity is destroyed. So now what we can do is we can give these quantities symbols so that we can work with them. So we have now We talked about the magnetic field. Okay, we've seen what it does. We can feel it. We know why it makes things get hot. We know what it does when we try to confine it or put it in a container. We've got that down. Same thing with the electrostatic. So we'll call the magnetism L, and we'll call the dielectric C. Now, the way we derive these is if I take a quantity of magnetism, which we worked with in an analogy, okay, and I take associated current flow that goes with it, that it drags along in the wires, it gives me this quantity L, which is called the magnetic energy storage coefficient. This is one of the most important quantities in electrical engineering. There's 4 of these. This is what I'm going to try to develop. L is the ability of this geometry to store magnetism. If I pack that space with iron, L is going to go up because I'll have more magnetism per the amount of current that I can detect by its movement against the wires. So basically, the geometry of the wires determines this energy storage coefficient. Now, with capacitance, it's the exact same situation. Because you have the dielectric flux, okay, and you have the electromotive force of the magnetism that's associated with it that gives rise to it, okay, and that gives us C, the capacitance of the system. So we have electricity is represented by the quantity LC. So now we recognize that from the Heaviside equation. This is back to that LC, whatever. I'll try to get back into that. So, but now we also have the magnetic field is dragging into the wires and causing them to get hot. So what we have now is we have an energy dissipation coefficient. Okay, and we'll call that R for resistance. And then the electrostatic lines of force have to terminate in the molecules, and that's agitating the situation and getting hot. So what we're going to call that is G, the conductance. So we have LC and RG. So basically, the heating of the dielectric field occurs mostly in the insulation and the insulators of the wire, and the heating from the magnetic field mostly occurs in the metal pins and the copper and all that of the electrical transmission system. The metal pins will get hot even though they are not in the so-called electronic-minded current carrying path. Is if there's any cycling or carrying on with the electricity, switching it on and off, the iron will get hot as well as the copper. So for alternating current, everything gets hot.
Were you suggesting a moment ago that electrons and protons have no rest mass?
Exactly.
Really? Okay.
They don't have mass at all.
Interesting point. All right.
I'll try to get into that, but then I got to bring up J.J. Thomson. And then we get in, not only do we have 2 fantastic stories to believe, but then we'll have 3.
That's a pretty interesting claim. I'm happy to hear your elaboration on that.
So basically what I've done is now, when you look up at the power lines, okay, it's not just some metal there. You now, everybody here can kind of get an idea that there's a dynamic, just like the thing with the car. When you speed up, there's a dynamic that occurs. Things move, things change, things readjust. And this is our basis for electrical engineering. And it's not complicated. It's actually very simple type of thing, as long as we have all these ideas, in our mind that were developed by Faraday and the people that discovered electricity. Okay, now what the Einsteiners tried to do was basically say that there is no electric field. It doesn't exist. Because all you have is the crossing point, which they call photon. And none of this other stuff even exists. It's just simply not there. Now, you just brought up the topic, so I'm going to get into that. Okay, the thing is the theory of relativity emerged from the writings of a guy by the name of J.J. Thomson and a few others. J.J. Thomson's the most important. J.J. Thomson revitalized the Faraday theory when the rest of the world was going back into the Newtonian action at a distance. To him, the lines of force were real, they were solid, they were there. I did an experiment when I was a kid. It's very simple, determined the same thing. I got a nice set of very sensitive, sound-powered Navy headphones from the Air Force Base. I had a magnetron magnet from one of their radars, and I had a 440-volt relay coil. Lots of turns of wire. Put on the headphones, connected to the coil, and waved it around the magnet, and I could hear the individual lines of force scratching through the windings. There was a fibrous something there. The faster I moved the wire through the air, the higher pitched the scraping noise was. So there was something scraping or acting, and to me, that is another experiment to establish the physical reality of the lines of force. Okay, now, the Einstein and the physics and all that, see, we're kind of back in the same situation now we were with Oliver Heaviside. The physicists said it was a diffusion problem and based all their work on that, where Heaviside said it was an electromagnetic, a double energy type of situation that had to be balanced. So again and again, these things repeated. So J.J. Thomson discovered a phenomenon called the electron. He is the one that gave us the concept of the electron. And here's how the concept of electron worked in J.J. Thomson's mind. Is in one of these electrostatic saturation conditions, let me take the inside of a radio tube or some type of deal where I've got two metal plates in a vacuum with 100,000 volts between them, so I have this nice intense dielectric field. Okay, it's straining everything. The plates are being pulled together. Okay, what it starts to do is if I keep cranking up the voltage, it starts to pull what it's connected to in the atom out. The atom can't hold it anymore. It's starting to yank out. So what happens is one will break. One line of force will break loose, and you will have what's called an electron at that end of line of force, because a line of force can't just break and end in space, according to the Faraday theory. So this end of line of force, now you have a rubber band of dielectricity that's snapping, okay? And its energy is being discharged in this snapping to the other plate, the positive plate, and that produces a physical action and a heat. Of course, now the Einsteiners said there are no lines of force, so all we have is the electron, which is a ball bearing that floats in empty space. And if we drop it to the floor, then we'll have electrons rolling all over the floor. But somehow that just doesn't work out like that. It doesn't seem to have any real mass. The mass is all related to the rate at which the electric field is moving. It has nothing to do with a physical object. Now, what was found was, just a second, what was found is that this electron phenomenon, if you try to make it happen faster, you cannot, if you have all the energy in the world, you can make it happen at the velocity of light. And anything less than that, it cannot reach that speed. And this is the basis for the proof of theory of relativity. The electron is not a ball bearing. Nobody knows. The only person that knew what an electron was Philo Farnsworth, and he wrote no books, and he's dead. Yes?
Well, the thing is, you mentioned about the cathode and all that. Now, if you have no voltage across it, the anode and the cathode, and you have the heater, because a cathode is a thermionic thing. With,
no, this is a cold cathode.
The cold cathode is a different thing. There's two phenomena that makes a cold cathode work. One is it depends on ions. Ions hit the surface of the cathode, and then electrons come off. That's what
that's after the breakdown. But you got to turn up the voltage to the point where the charged carriers get pulled out of the metal.
Yeah, well, they call that brute force field emission.
Yeah.
Which is where
thermionic emission is where you heat this plate up to red heat.
Yeah.
So the electrons can't hold on very good anymore.
Yeah.
And you can just heat it up to the point where the electrons just kind of boil around the whole thing, but they got nowhere to go because their lines of force are all going inside. They're not outside.
But it also results in the cooling of the cathode. The cathode is actually
it's actually on a field emission. Tesla showed that when the anode gets hot, the cathode refrigerates.
Yeah.
Which is kind of a remarkable thing in itself. So what led out of J.J. Thomson's idea was, when you read his book, which is very simple, those mathematics is kind of shoddy, but there isn't a lot of it, is that here's the implication of J.J. Thomson's work, okay, is space is filled with electricity. We don't know what the voltage of the planet is with respect to the sun. We can't just say right off the top of our heads what the magnetic field intensity is in this, but at any rate, if I got my car sitting out in the street, it's being that it's metal, it's got all this electrical lines of force attached to it and surrounded
We're just going to go back a minute here. He said something that Tesla told him. The anode and the cathode. One's really hot. The other gets super cooled. So let's listen again and we'll talk about it for a second.
That when the anode gets hot, the cathode refrigerates,
Yeah.
which is kind of a remarkable thing in itself. So what thermionic emission is where you heat this plate up to red heat,
Yeah.
so the electrons can't hold on very good anymore.
Yeah.
And you can just heat it up to the point where the electrons just kind of boil around the whole thing, but they
Yeah.
got nowhere to go because their lines of force are all going inside. They're not
Yeah.
outside.
But
There's
it
no
also results in the
polarization.
cooling of the cathode. Cathode have actually.
Yeah, it's actually,
The
in
cathode
field
would
emission,
actually-
Tesla showed that when the anode gets hot, the cathode refrigerates.
Yeah.
Okay. Now that we heard it, okay, we always talk about vortexes. What's the main thing to know when you have one? That one side gets hot, the other side gets super cooled. There it is. You
Yeah,
pull the
that's
energy into
interesting.
the ether. Go ahead, Ben.
No, I was just saying that's interesting.
Have you guys heard of a Peltier device?
No, I haven't.
It's an electronic device where when you, it's a sandwich layering. When you apply electricity to it, one side gets hot, one side gets cold, so you can stick it between your processor and your heat sink.
Wow.
Supposedly help cool. Anyway, yeah, one side gets hot, one side gets cold, and they're little thin things you can buy. People build these really cool, I think, sonic refrigerators with them and stuff. They're pretty neat.
Interesting. Yeah, I just thought it was a good point because we're always talking the coil, we're always talking the center cold, we're always talking the outside hot. And it proves out in theory, it proves out in the work that we're doing that it's always that way. It's always got a loss in
Yeah.
oh, sorry, what was that?
I'm just reading Mr. Lane's.
Oh.
Lane's?
Okay. Sorry, now I'm lost. Okay, anyway, all I was trying to say is it was just interesting that Tesla would tell them that, and that it would like hit them in a different level, but it hits us just right because we're dealing with it all the time. So, cold electricity, the whole thing gets cold on one side because they're not equal, not in a DC flyback anyway.
On that point, you're familiar with Master Evo? He has in his like associate guys videos that he talks to, there's a man that does plasma discharges on toroidal magnets, and he shows how the poles where you put the charge, you can get a cold plasma or a hot plasma. And he actually proves it because he's got these wooden matches, and the plasma will not light in the cold zone, but in the hot zone, the piece of wood starts on fire.
That's really cool.
Tesla said if you could do the right frequency, where the electron did not get so excited that it went off in a stray orbit and you lost that energy, if you could just spin the electron up into the sine wave to the 0 point and then down to the next 0 point, where you throw a ball in the air, it stops and hovers for a moment, that's your 0 point. If you could just get them pulses, the electron would not dissipate. So you could play a frequency into a flame, and he said you could generate a rigid flame that would not lose energetic potential. So the flame would stay solid and rigid, and you could wave it around. That sounds familiar from movies.
Yeah? Huh. Give me a second. All right.
That's how you make the lightsaber.
Yeah, that would be
It's in
interesting.
one of his
Wouldn't it?
books. Bernie has the same book, The Fantastic Inventions of Nikola Tesla. I could find the article while you continue. What page it's on, you could actually read it.
Oh, right on. Yeah. Let's see that.
It's in that
If you don't
book.
mind. Huh.
It'll probably take me a few minutes to find exactly where that one was.
Okay. Yeah, not a problem. All right, let's go ahead and play a little more dollars while you're looking that up.
In itself. So what led out of J.J. Thompson's idea was, when you read his book, which is very simple, those mathematics is kind of shoddy, but there isn't a lot of it, is that here's the implication of J.J. Thompson's work, okay, is space is filled with electricity. We don't know what the voltage of the planet is with respect to the sun. We can't just say right off the top of our heads of what the magnetic field intensity is in this, but at any rate, if I got my car sitting out in the street, it's being that it's metal, it's got all this electrical lines of force attached to it and surrounding it. Okay, now according to filled with electricity, we don't know what the voltage of the planet is with respect to the sun. We can't just say right off the top of our heads of what the magnetic field intensity is in this, but at any rate, if I got my car sitting out in the street, it's being that it's metal, it's got all this electrical lines of force attached to it and surrounding it. Okay, now according to J.J. Thompson, that is the reason why when I slam on the brakes, the car doesn't come to an instantaneous stop. It's because the electricity has to discharge. So J.J. Thompson's idea was, if you took and found a way to make the voltage and the current associated with the metallic body of the car equal potential of where you stood in that place in the universe, so all the lines of force detached, because there's no difference of polarity, that you could step on the brakes and the car would come to an instantaneous halt. And basically, velocities and all of those things would almost lose their meaning because there'd be no restriction to the movement. Now, the problem is, okay, well, that sounds good. How do we begin? Well, the Einsteiners tell us there is no universal ground or neutral wire or point of rest or any of that type of stuff. So we'll have to give up at that point. But at any rate, someone pointed a gun at our head and said, no, you're not going to give up. You're going to figure it out. So what we'll do is, well, gee, Tesla came up with this unipolar idea where he could ground in the counter space. Well, what would lead out of that is the Tesla device could be phased or tuned in such a way that its counterspatial neutral would be at a universal grounding point. And grounded against that, then your vehicle would have no potential because it would be grounded to this dimension, and all the electrical lines of force would disappear. Now, as a lot of people believe that the Germans developed that in aircraft, and the United States glommed onto all of them during World War II, and they did indeed disappear into Bell Telephone and some weird place in New Mexico. I can't pronounce the name of. Who knows the name of that? Algamorado or? Okay, yeah.
So, all right, hold on. So if you made your ether the ground and you made the pump go against it, that would be the only way that you could do it anywhere you wanted to. You don't have anything else. Everything else is different. It's the only consistent thing in the earth. So if that's what you had and that's what you could do and you can violate it in the law, then you'd have to pump the ether in every planet, and every planet's ether would be different because it's set to a different frequency. So that would start to make a lot of sense. You just have to learn a little bit more. That's it. So, but you can't imagine things to be real. You got to prove something. You know what I mean? You got to prove that the pump's working. So, I don't know. Pretty interesting.
The contention is that all this talk of aliens and UFOs and all that is just a weird type of compounding disinformation story where they actually throw the material out and then deny that it exists. So the whole thing just becomes a self-consuming lie, and nobody realizes it's really actually Earthlings doing this stuff. But of course, that's all Art Bell world. So I won't get too hard into it. But these are all the things that pop up when you get into this electrical world. And it's my conclusion that that's the main reason why all electrical research has been stopped and swept up. This because the possibilities are incredible, absolutely incredible. So, some more questions.
Well, speaking of Art Bell, because he had his parallel line loop antenna, do you think because of that particular configuration, and he had this other space between those two lines, that's why he's picking all that voltage off?
No, the reason he's getting all the voltage is because it's a great story. Art Bell is an entertainer. You've seen the same piece of loop of wire, you've virtually touched it at my place, and that's just not happening.
But they did have this very long, exactly parallel matched loop. I thought maybe that configuration matched your model for the dielectric field in between.
No, Art Bell is an entertainer like Michael Savage.
And my last question would be, just to make sure I got this, because I'm still trying to figure this out. You're suggesting that protons, electrons have no rest mass, but that their apparent mass is a function of the velocity of the force lines. Is that correct?
Right.
Okay. It's a theory. I'm digesting it, but it's interesting.
Yeah.
Before you ask the question, could you elaborate on your last statement? The information about electricity being gathered up or whatever.
Well, if you look at electrical history, okay, you can see it was just a ball of confusion for 300 or 400 years in Europe, where such things were observed. Obviously, the Hawaiians and the Aborigines weren't doing much experimentation. It all came out of that neighborhood, and then it just boom, took off. Twice it became, with Franklin, it became almost like a fad that everybody in France was wearing lightning rods on their hat. I mean, every phase of electrical advancement resulted in this social reaction of complete amazement and partying, like when the telegraph line was finally sent across the ocean and all that. It was massive effects. There were riots on the street when Einstein and Darwin presented their theories to the public. See, all these things have disappeared from the history books. So you go through and you see, if you read, what I did is I read all the minutes of the American Institute of Electrical Engineers from its inception to the death of Steinmetz, page at a time. I went through everything, looking for, qualms, so to speak, little goodies, things that I could, get something out of. There was one meeting where all these guys were together, and they felt that within a matter of months, with Steinmetz's work and Tesla's work and all the stuff that was being discovered by Heaviside and all these other people, but it was a matter of months before a rotating apparatus was going to be built that provided electricity without requiring a prime mover. It's right there in writing by the chairman of the meeting, Professor William Anthony.
And what happened? Why?
It just basically step by step, because of the physicists and the Einstein and all that, just got chopped and chopped and chopped until eventually electricity has been declared impossible to even exist. Every device that hangs on those telephone poles now, every electrical device you have cranking or whatever's going on in your car, any electrical device that's pulling the elevators up and down, running the blowers, powering these light bulbs, or any of that stuff at all, was all invented by Edison and Tesla and a few other guys.
Who was doing the chopping?
Well, I don't know, figure it out.
Well,
All I can do is speak from experience, okay? Everything I've built has been destroyed.
right.
Let me finish. Okay, I'm just going to speak from my experience, okay? Everything I built has been destroyed, okay, as people have been hounding me and harassing me my whole life, ever since I was 6 years old, even before I came up with anything. It took a while to figure out why all this worked, okay? And I won't get into it, but I'll get into the specific example, okay? The thing is when I was a child, okay, I wasn't interested in riding bicycles or kites. I didn't need to go goo goo gaga, see Dick run, see Jane run in the classroom, because I was too busy reading my father's naval and electronic engineering books. That's how I learned to read. I just sat down to open the books and read them. I don't know where I learned how or whatever, but that's immaterial. That's just what I did. I probably got enough out of the kindergarten class or something. Okay, when I was 12 years old, Pacific Gas and Electric took me on in a private tutoring special education situation. Okay, and then the phone company came next. Once I had all my federal licenses when I was in high school, the phone company came in with a couple of spooks that looked like some CIA guys with, the gun in their pants, but not quite, where's Eric Dollard? And it was a couple of stunts that me and my buddies pulled the week before. I was not feeling happy. And they go, we want you to attend this meeting, special meeting. And it just kept going and going like that. And then RCA came in Bolinas. Okay. And when I was 17 years old, I was completely absorbed into the station. I could come in there any time of day or night, get parts I needed for experiments, had the keys to the gate, so we could party on the beach, all these type of things. Okay. RCA, the phone company, 1970, what me and my friends called the day the music died. Okay. All those companies started going down like that. So what I did is I managed to glom on to a couple of corporate engineering executives in these companies, okay, and told them what I had set out to do, electrically researching, and I had the full backing of these big corporations. RCA gave me all of their equipment in Bolinas, except what was actually online. 25 tons of apparatus.
Wow.
To do what?
For my research. Transformers that stood 7, 8 feet high. There's a few people here that were with me in that episode. Actually, only one person. I don't know where she is right now. But that's it. Nobody, that's all gone. There's no see or belief or anything. An environmental organization came in, seized the whole situation, hired high school vandals to smash all the equipment with hammers and axes, spread the mercury and the PCBs all over the floor, the environmental saviors, smashed everything, cut all the cables, dumpstered all the notebooks, tried to make sure I had no place to live in town.
They were hired by.
No, they own the place now. They just simply took it over and then pushed RCA, what was left of it, to the other side of the wall.
Yeah, but they were hired by other people who were hired by other people.
Well, I don't, that's all for that's for you to figure out. I'm just leading the trail. You go talk to these people, okay? You go to Bolinas and you go to the RCA station and they call themselves Commonweal. You talk to them and get their story. That's how you deal with those type of people.
Well,
Okay, they managed to
they
get
were hired by other people.
So at any rate, let me continue. I don't know who, I'm a scientist and an engineer. Okay, I can't speculate, otherwise I just burn my whole life up chasing UFOs and space people and Soviet Tesla scalar conspiracies. You know what I mean. So what it finally evolved to is a guy and a friend of mine got together with me and we went with a videotape camera. Okay, and went out into RCA to get pictures of the last of the antenna field and everything before it was finally smashed down. Well, in the process of this, by some weird turn of events that I won't get into because it sounds like voodoo, it finally resulted into the chief park ranger himself, Mr. Sansing, searches the entire 3,000-acre antenna field, which has been my personal rat hole for 30 years, to find the hated Mr. Dollar. And he finally does. He finds us down in the ravine, taking a break, where the deer hang out. Not easy to find. He must have took him at least an hour, worrying about tire pungees and low-hanging wires and the whole thing. And they found me, and he did that so he could come up to me and say, quote, Mr. Dollard, there will be no more electrical research done here ever again. Do you understand, Mr. Dollard? You know what I told him? No. And it didn't stop there. So you figure it out. All I know is it's just, it's that percentage of carbon monoxide in the air that I got to live with.
But what about all the hidden budgets now in the executive branch of the federal government?
I don't know anything about that.
Oh my God. They can take all your research and turn it towards military.
Well, good. Let them blow up the world.
Well,
They're going to do it anyway. Have you heard about the National Ignition Center? Oh, it was on KNX News in Los Angeles. We had a whole party about it in Bolinas, amongst a couple other issues. What they're going to try to do is set off a nuclear bomb and contain it in the East Bay in one of their laboratories.
where?
Little worse. Yeah.
All right. That goes a little far into stuff, and I'll let everybody watch that on their own. You really got messed with, man. That's too bad. That sucks. Damn, people coming in there messing with you. I don't like
Yeah.
any of that stuff.
Yeah. Yeah, me neither.
Which one was that?
Oh, I put it in the comments here. Let me see what it says. Let's see. It says
That wasn't the transverse plus longitudinal equals superluminal one, right?
no. It's Eric Dollard, History and Theory of Electricity.
All right, guys, I'm gonna get going. I appreciate everything, Nathan, and the Sears. I appreciate everything. You guys take care, and I'll see you
Right on,
tomorrow.
Ben. Thank you.
Have a good time, benefactor.
Thank you. You too.
Is there anything you want to talk about, Victor, before we all take off?
No, he's given me a couple of points that I got to look at. Like I said, I got to cross product that then, and tear apart that 1/137 and open it up.
Nice. Yeah, there's a lot there, man. I really like Dollard and what he does, man. He really kind of gets into it and tells you things. And he really not holding back too much, except for, his personal stuff there.
Which of your videos would be best for me to start to find out what's going on with this puppy? Because I read there's something about starting it that I'm going to have to be careful not to burn it out. When I bought it said something about start voltage or current and shit. Which one should I watch to?
Well, what are you trying to do? What are you making out of it?
I'm going to redo this 48-volt power supply and hook it up to get ready for some rodent coils. I might fire a Tesla up with it and my spark gap. I don't know. But I was thinking of putting it on a coil, but I don't want to burn it out.
Yeah, you want to probably start with 12 volts anytime
Right.
you put it in there. Yeah. And then that's where I would do. 48 volts is quite a bit. They tend to not like that. Though they do handle up to, oh, God, what was it, 40 volts is what I put into one, but it's only for a little while. Once they get too high, they tend to, MOSFETs just go. They get too high.
Then I'll start on the Sigilant then instead of the big one. What is it everybody's saying? Don't be afraid and go 50 volts. Is that a larger ZVS or?
I don't think that's a ZVS at all. It had to do with a motor. They were talking about a pulse motor with Mike Faraday was talking about that.
Okay.
So kind of a different situation altogether. I don't think it ties into that particular point you got there. Yeah, one of those with a trigger circuit, you could actually, it's just a little cheap device. I got one right here. Basically, all it does is this little circuit will take and allow you to put frequency over top anything that you want inside that. So if you got a frequency generator and you put it on this, there's a low end and a high end. So the high end just deals with the power. So say you put 12 volts in or say 20 volts in, and then it just goes through. You go into one side of this and out the other. It's what?
I can then modulate the power?
Yep.
Or is
then
it just running as a carrier?
So what it does is it adds a carrier wave to it. So it basically allows you to change the frequency and it allows you to change the duty cycle. So you could do both of those and then it'll change that whole coil experiment completely. So it just gives you a little bit more. And then also it gives you a cheap component in the middle that you can explode instead of your whole receiver or anything else. You got like an $8 part here versus, $40, $50 receiver. Makes all the difference in the world.
Okay.
So this one, I think, this little guy right here is rated up, I think, 48 volts or something like that. So you'd be just fine if you had one of these. And then you could put whatever you wanted to in frequency in there.
Huh.
So that's what I would do. So that's what I plan on doing with my coil. I'm going to put that on there with my little driver. I don't even think I need a ZVS for that. You could do it with ZVS if you use a flyback. stuff like that, then the ZVS would run your flyback, but it also changed the frequency and the duty cycle of it. So this little circuit's just a trigger circuit. Let me see if I can't pull it up on Amazon real quick for you.
Yeah, maybe a link to it.
Yeah.
Okay, then. I guess I will be trying to figure out the pinouts of that old school flyback.
Okay, give me 1 second. I'm looking it up. Oh, here we go.
Says 619 on the bottom. It's a great big old flyback.
Yeah, you got an AT flyback right there from a TV.
Yeah. Is that the wrong kind?
No, it'll work, but when it comes out, the voltage comes out. It's not going to be very heavy. You have to get a voltage multiplier to go with it if you want some real voltage.
Oh, and that's the capacitor stack you guys been building?
Yeah.
Okay.
So, yeah, because it comes out maybe, I want to say it's this long right here, maybe half an inch or so. That's about all the spark you're going to get out of it, which if you put it into a coil, it might be just fine. But if you're looking for some high voltage experiment, it wouldn't be. So
No.
you have to get the multiplier.
No, I don't really want to throw energy away and do sparks. I want to test with different values of electromotive force and check that pressure.
Absolutely. So, yeah, then you're fine. Just watch what you put into it. Okay, let me see. I'm getting the link right now. Oh, man.
It's amazing. Each time I watch Eric's stuff, something different pops out.
Yeah.
I guess you get what you need when you're.
So let me see right here. Stop sharing, present, share screen. So this right here is the circuit. So it says it's 600 watt.
Dang.
So yeah, it's going to handle a little bit for you right here. 0 to 24 volts, it says. Let's see. So yeah, it'll be a pretty good circuit right here. Output captivity DC 4 volts to 60 volts, 10 amps. I don't know that it runs that high, but it's pretty good. The little one I had, like this, it was doing 24 volts at a couple seconds. You know what I mean? And then it heat up. But then when you ran 12 volts, it like ran all day. So this one right here is a bit heavier, so it'll probably do better than that. But like I said, it's a trigger circuit. So if you look at it on the left side of it, the power goes in, the power goes out. That's as simple as it gets. On the right side, frequency generator. And then you could do whatever you want. That's why I have one for, coils and stuff like that. So
Cool. That's cheap enough to get a few.
yeah, knowing me, I'd probably blow them up. So I bought a few when I got them. Oh, man. All right. So we'll stop sharing that. Hopefully, I put a link in the description, guys, if you wanted to get one of those and try it out. But that's where my experiments are going. So I'm going to be trying that out. Man, your dog's all over you today.
Oh, yeah. She just got brought in. She's happy. She just turned 6 months old today, lost one of her little canines. And so the pain isn't there so much.
Oh,
New teeth are coming in.
nice. Right on. All right, guys. Anything else, Victor, before we take off?
Nah, I'm going to do some playing and checking.
Right
Get
on.
ready for Wednesday.
Yep. I got to go cook for the family right now, so I got to get going.
Yeah.
All right, guys. Thank you, everybody, for showing up. Victor, thank you for showing up today. And I want to thank Ben for coming in and checking things out. Guys, thank you for hanging out with us. I really do appreciate everything.